All right, we can go ahead and get started. So first of all, thank you very much everyone for coming back for part 2 of this webinar series. We hope you enjoyed the first part and also were able to actually access all of the exercises and whatnot. There were a couple people that were still having issues this morning accessing everything. So we're still working on that. Hopefully we get it resolved so you can actually access everything. But we'll go ahead and do things the same way we did last week for part 1. Please make sure that your microphones and cameras are turned off, just so that we don't accidentally get any background noise or anything. Same as last week, if you have questions, please feel free to drop them in the chat. And then throughout the webinar, I'll do a few small Q&A sessions to make sure all your questions get answered. So with that, I will go ahead and turn it over to John and we can get started.
Thank you, Colleen. Well, everybody, welcome back. We are going to pick up where we left off last week without breaking stride and take you from your rudimentary understanding of the TensorFlow framework and basic neural nets. And we're going to, by the time we're done here today, advance ourselves a lot further, and we're going to be doing really good vision recognition as opposed to our very simple thing, using the techniques that are used in current leading edge research and production neural nets. In particular, we're going to be using convolutional neural nets to do a much better job of our image recognition. And we'll see how we're going to do all of this in the next hour or so. Last week, as we left off, we were, I hope, comfortable with the idea that neural nets, deep neural networks, are essentially these layers where we have an input layer, an output layer. The input layer, in our case, are images of characters at the moment. So they could be much more complex images with much more complex included subjects. Our outputs, in our case, are going to be classifications of digits from 0 to 9, but they could be much more complicated. They could be transformed images, and we'll see the kind of networks that enable this more complex behavior to occur. But at the moment, we're going to focus on advancing our MNIST problem that we used last week, our digit recognition problem. Now, the exercise from last week was to identify some hyperparameters in the code and see if you could improve the performance in any way with those hyperparameters. Hyperparameters, as I said last week, and as we'll demonstrate continually this week, are really the fundamental research issue and effort sink when you're developing a neural net, because it's easy to come up conceptually with an architecture of a neural net that you think might be good, but tweaking all of those hyperparameters to make it work effectively can take a lot of research. The hyperparameters that we have in our very, very simple regression MNIST version here are few. We'll see how quickly they multiply as we get into the convolution, but essentially they are the step size of our solver. So our gradient descent solver, as I said, you can visualize it as it's marching through space trying to find the smallest error that it can possibly find for all of these weights. And the steps that it takes as it finds that small error, step size is one hyperparameter. And if you pick too small of a step size, it will take you forever to train the neural net. If you pick too large of a step size, it might not find the best solution or even a good one. The other hyperparameter that's obvious here is how long we train. And how long we train is basically how many of these mini batches we grab. So in other words, how many times we go through all the training data. And that's composed of our for loop on the outside that says we're going to grab 1,000 of these mini batches of 100 to train this neural net. And you might find that, you might suspect that, what if we train for 2,000 instead of 1,000? Will our accuracy improve? In general, that's a reasonable assumption. In this particular case, not so much, because our network's so simple, it's just about as good as it's going to do. And the mini batch size, how many of the samples do we grab at once before we send it back to the trainer to try to improve the weights? That can have an effect too. If you pick a very large mini batch size, you might expect that you're giving more accurate sampling of the data to the solver to improve itself, but you're also having to do a lot more work before it gets to improve itself. So a balance there is something that you achieve through inspection and experimentation. In our case, nobody was really able to do a substantial improvement over the simple network playing with these hyperparameters, although one of you did go above and beyond and actually added in a hidden layer of neurons, a whole new layer of neurons, and then that you were able to get, that person was able to get their results up to 96, 97% accuracy. But that was more than I expected you to do. I applaud your efforts. And as you'll see, that only really takes a couple of lines of code. We're going to do that ourselves as we expand our network. But I didn't expect any of you to actually go that far. But that did result in an improvement of getting things up to 96 or 97% accuracy. But we're now actually into the realm of real neural networks when we start adding hidden layers. So let's look at what an architecture might look like for a real effective neural network. In particular, a convolutional network. We haven't discussed convolutions yet. We're going to get to that in the very next slide. But to get ahead of myself a tiny bit, give you a preview of where we're headed, this is what a more realistic and effective architecture might look like for a neural net that's doing real vision recognition problems, where you've got a real interesting image with a lot of detail to it, and you're trying to figure out maybe how to classify multiple objects and their positions. It starts to have a lot of layers. And each one of those layers has multiple components to it called convolutional kernels, which we'll look at in a moment. So this just gives you some idea of how we can start to take these building blocks and add them together and make more complex architectures. And believe me, we'll understand exactly what's going on here shortly. But this just gives you an idea of why this next piece that I'm about to introduce is an important building block. It's the building block that makes up all of these layers here. And that next piece is the idea of doing a convolution on an image to process an image. So far, what we've done is we just throw all of our pixels with our simple solution, and even with the more complex solution that you might do without convolutions, is we throw all of our pixels at input neurons, and we start working from there, treating all the pixels as though they're independent from each other. And in reality, if you think about an image, you recognize an image has a 2D structure to it. So just throwing all the pixels as one big vector, as in our case, we've got these 728 pixels that we're throwing at this image, or 746, whatever it is for our 28 by 28 image, we're stretching out all the pixels and just throwing them at the input level of our network. But you might think you're wasting this fact that the actual image is a two-dimensional image. It has structure to it. It has relationships between pixels. It has relationships between objects in the image. And to throw all that out seems wasteful, and indeed that is the case. So convolutions are, I was about to say one approach, but it's by far the dominant approach to deal with the fact that when you have structure to something, you might like to take advantage of the locality of that information, the fact that pixels are related to each other geometrically. And a convolution scans over an image and applies a function locally to figure out how to pass along the next image in that pipeline. So here's the very simple mathematics of it that we'll illustrate it at the most basic level, because the mathematics, once again, are very, very simple. As I hope you recall from last week, the mathematics of neural nets for regular fully connected neural network layers are very simple. They're basically add and multiplies that you just keep stacking together. Convolution is a variation on that, but it, once again, is very, very simple mathematics. A convolution scans over our image. So this is our input image. It's only a 4 by 4 pixel image here, so it's a very small piece, or you can think of it as a piece of a larger image if you'd like. So we've got a very small 4 by 4 pixel region we're going to scan over, and we're going to scan over it with some convolutional filters. And so this first filter up here that we might scan over our image to do something on that image. We'll look in a moment what those somethings might be. But this first filter that we're going to scan over this image basically does this mathematics right here on the bottom. It's very simple. It basically says define this new pixel here in this output image. What we do with this filter is we take and scan over this region of the image here, and we just, for each one of these elements in the filter here, we multiply it by the input value in the image, and then we just do this operation on all 9 pixels here. So we've got 9 different multipliers. We apply it to these 9 different pixels. We add them together, and we get the new pixel in the result and output image right here. So it's very simple mathematics. Once in a while, you hit the image, the boundary of the image. For a large image, this is a tiny bit of the time, but you have to deal with what to do on the boundary. And the normal thing to do is just to pad the boundary out with some zeros here, pretend there's some zeros, and that makes the math work out very simply. So it's something you need to worry about, but it's very straightforward and simple. So you might be asking yourself, okay, what do these convolutions do? Well, the answer is that they can do some very powerful transforms on the image, as simple as they are when they're applied over the entire image. They can do some transforms that allow you to start to extract some interesting information from the image. So here is an edge detector transform. So our kernel would have these 9 values here, but we're a 3 by 3 pixel transform. If we slide this transform right here over this image, so So we're given this as an input image, and we slide this transform over the entire image, and this is our output right here. You can see that it's called an edge detector for a reason. This particular edge detector does a pretty good job of detecting edges, in this image. And I hope you find it impressive that this very simple mathematical operation just done repeatedly over the entire image does such a good job of finding what do look like there are the edges in this image. So this is the classic approach to doing image processing using convolutions, which certainly predates neural nets. And is the standard thing that you found in a camera back, or in Photoshop for that matter, back in the 90s, before anybody was thinking about applying these things in neural net terms. There were a handful of convolutions that were very good at doing these kind of things, for doing edge detection or blurring images or sharpening edges. And these were constructed by hand. We're going to find out that our neural nets learn how to do these things. They learn a bunch of convolutions which are useful, but you can see how even the simple hand-constructed ones can be very effective at extracting information out of an image. And we could pass this along then to a neural net's next layer, and it has the benefit of knowing where the edges are in this image. So now it can start to determine shapes or orientations of things and whatnot. You can imagine for MNIST how this would be very useful for it to be able to figure out where the edges of the numbers are, so it can now look at them in a much simpler version than its kind of fuzzy grayscale images. Okay, well, if we've got these convolutions and we apply them to an image, we could draw it out like this right here. This is our input image, and we apply this convolution A across the image. You're going to end up with an output that's learned something interesting about the details of the image. And we can pass those along then to a fully connected layer. So that's what F stands for here, fully connected. Often that's abbreviated FC. So we can pass these things along to a now fully connected layer. In other words, the neural nets that we've been looking at so far, which are just all the neurons are connected to all the neurons. They're not this subsampling convolutional approach. So if we go from our convolutional approach to our classic fully connected layer, we'll find ourselves with a pretty good architecture in that this convolution finds some details, and the fully connected layer is smart and can put the details together. So we've got these two kinds of building blocks now to work with. Either the fully connected layer, which has a lot of neurons connected to a lot of neurons, or the convolutional layers, which are the small number of filters that scan over the whole image and extract some information. And typically, at the end of a network, a convolutional network or any network, we have these fully connected layers because they're really smart. They have lots of weights and they have everything connected to everything, so they can learn a lot of abstract information. And on the input side, we'll have, or upstream, closer to the input side, we'll have a bunch of convolutional layers because they are capable of scanning the whole image with a small number of weights and extracting some information. So the trade-off is they have a small number of weights to train, which is useful, but they can scan large images. These have a large number of weights. You can remember from last week that a fully connected layer of 1,000 neurons collected to 1,000 neurons has 1,000,000 weights to represent all of those connections. And 1,000,000 weights is a lot of weights to adjust and train and figure out the proper values for. So fully connected layers are expensive, but really smart and flexible. Convolutional layers are a lot cheaper and can scan the whole image, and they're powerful, but they can only learn certain specific things, like edges, for example, with one of them. So the combination of the two is pretty powerful, and what we'll see is the standard architecture we're going to use. What we'll see is standard, and I was shown in that first picture I showed you of a typical convolutional full network or application, is we stack these things together. So this first layer here might find edges. The next layer here might be good and learn how to do things like find shapes, circles or squares or boundaries on things. And we might have another layer that we could stack on top of here that begins to recognize how those shapes collect together into eyeballs or arms or things if we're trying to recognize people. And so we stack these layers. Each layer learns more details at a higher level. So we go from at the lowest level detail here, what's often called style, and I'll show you some examples of that, up to the higher levels, which are sometimes called content, the things that are actually in our images. And at the end, we finally feed these through to a fully connected layer, which tries to put all the pieces together and say, oh, you found some eyeballs, and you found some arms, and you found some legs. I think that's a person, or I think that's a horse. And so this fully connected has the ability to put all the pieces together. Okay, let's make sure we're comfortable with the idea that we can have multiple kernels on each layer determining multiple things. So even on the first layer, where we've got all the fine detail out there, we might have some that are edge detectors. We might have other things that detect maybe big differences in color. Some of them that detect maybe vertical edges or horizontal edges. So we can have multiple filters on any one given layer. And let's look at how that might work here in the case where we're going from a layer where we have 3 filters applied to it to a layer where we have 2 filters applied to it. We get to pick how many filters we want to apply to each section of our pipe as the image is being processed. This is a hyperparameter that's very important to make things work effectively. We'll come back to the idea of how might you select that number, and the answer once again is it's experimental. There's no right answer or wrong answer there. There's only the one that's most effective. So you as a designer of a convolutional vision system have to pick on each layer how many kinds of filters you want to have. And so in this case, we're just going to look at the mathematics of having 3 filters on one layer going into the next layer where we decided to have 2 filters, just as an example. So this incoming volume here, part of the pipeline, has 3 filters giving us information. One of them might be an edge detector, one of them might find vertical lines, one of them might find horizontal lines, for example. So it's giving us these 3 volumes. We decide on the output side, the next layer, that we want to have 2 filters working away. Maybe we want to have at this point filters that start to put things together into circles and squares, for example. So we've got these input layer, this output layer. What's the mathematics of how our convolution step through these images and process it? It's pretty straightforward. It's the same thing that we looked at simpler with the one convolution. It's just we have to keep track of multiple operations going on. So in this particular case, to find this value in the output volume that we've got, we're going to have 2 output. We're going to have 2 different volumes coming out here for 2 different filters. We've decided that. Again, these are hyperparameters. We get to pick 3 here, 2 here, 5 in the next layer. So we're picking 3 and 2. So that means the mathematics are going to work out like this. We've got to find out this number here on the output layer here, 4. What we're doing is we're applying this convolution right here, this filter right here, to this volume of data. And if we do all the additions and multiplies here, 1 times 0 plus 0 times 0 plus 1 times 0, we do all the math here of this one, and this one, and add them all together, we'll find out that we end up with the value 4. And you could step through there and do that if you don't believe me, but these are all adding up to be equal to 4 right here. Then we want to find out the next element in this output volume here. We do the same thing, but we've shifted over the convolution here. We've decided to shift the convolution to skip it 2 at a time here. So if I go backwards or forwards here, you can see this convolution happens to be skipping 2 at a time. That's one more hyperparameter that you get to pick in your application, the stride of the filter. The filter could move 1 pixel at a time. That might be nice and get us information at a very fine level of detail. We might want to skip it bigger chunks at a time. We might want to kind of have a little bit zoomed out of a picture and find grosser information. That's a hyperparameter. We have to pick it. So in this case, the hyperparameter chosen for this was to have a stride of 2. So our filter's jumping along in chunks of 2 here. And if we look at what it's doing at any point in time, it's always doing the same math that we outlined at first. It's basically saying, okay, take this element times this one, take this one times this one, take this one times this one, add them all together, and we end up with the output element here of 11. So the mathematics are very simple. It's just we're starting to build them up in layers, which make it seem more complex. But really, again, I hope all of you can follow along with the basic mathematics at the bottom of it. TensorFlow allows us to very casually add these things up and build up complicated layers. So it's easy to construct things that are much larger than even this example we're looking at, but I hope you all feel comfortable understanding what's going on at the fundamental level. Okay, so this is how convolutions scan across an image and generate output volumes from input volumes. So it's up to us to pick up, to design some architecture. So the mathematics of what we just looked at from the layers going from one layer to the next are very straightforward. We have a bunch of hyperparameters, though, that we have to pick in order to do this. We have the number of filters that we want to apply to each layer. And again, you might say, well, how do I pick that number? There's no right answer, wrong answer. And we'll look at an example, and then it'll become a little bit clear that you can maybe get some guidance from a similar application or somebody that's doing something similar to what you want to do. But it's up to you to make sure that that's really an optimal number, and you might want to experiment with that. The size of the filters is up to us. We've shown you an example so far. The previous one was 3 by 3. We can go larger. We'll see some applications where it's 12 by 12. I think the one we're going to use for MNIST is 4 by 4. So the size of the filters, how big the convolutional filters are, is up to you. How much they jump from one pixel to the next is up to you. That's the stride. The padding is pretty much boring. It's just pretty much how do you want to pad on the edges. That's not so much up to you. There's pretty much most of the time you just want to pad with zeros and maybe not. Anyway, when we do these operations here, we go from an input volume that's got a certain height and width and height, so the resolution you can think of it, and depth, how many filters we have, and we end up with an output volume that has a new width and height and depth. So typically it's shrinking down as we have more filters process the image. We're zooming out, so we're shrinking it down. And the depth, how many filters we have at each level, varies a whole lot, and that can increase or decrease depending on how useful we think it is to capture a lot of details, different types of details at that level. So here's the mathematics. I hope it makes sense to you, although you certainly don't have to peer at this slide too strongly right here. More importantly is to understand the idea that we're stacking these layers. And if you think of stacking these layers, we want to go from the low-level detail to the high-level detail. We want to zoom out on the image or go to kind of a lower resolution intentionally as we process these images to go from recognizing edges all the way up to recognizing horses and airplanes. This zooming thing is something that we might want to even accelerate instead of just doing it all through our convolutional filters, gradually shrinking things down. We might even want to zoom out by basically just zooming on the image like you would if you were resizing any image in Photoshop or some graphics application. And the way we do that is what's called pooling. We take and we just quite literally zoom out on the image by subsampling the pixels, sampling the pixels down. And so just like you would do in Photoshop if you had an image that was 1,000 by 1,000, and to put it on your web page, you want the resolution to be lower so it would load faster, and you want to zoom it down to 500 by 500. What would you do? You'd take every 4 pixels and you'd combine them together so that you end up with a 500 by 500 image. That pooling operation is something that is important to do in convolutional networks. It's very effective at letting us zoom out. And so that's one more operation. It's the last one we're really going to have to add in here to our network in order to do some good image processing with convolutions. So that pooling operation can be done in several different ways. You might think that the best way to do it would be like in Photoshop. You'd probably, if you had 4 pixels and you want to turn it to 1 pixel, you might average those pixels. Or if you're more experienced with graphics, you might realize that there are other more complex sampling schemes that give you even a more satisfactory image, like bicubic sampling or something like that. But in the case of neural nets, we use something very often. There are different options available to you in TensorFlow. The one we're going to use is probably the most common one, which is called max pooling. And that is to just take the maximum value, the pixel that has the highest value of those 4. If we're zooming out 2 by 2, we'll take of those 4 pixels, we just keep the one with the maximum value. For straight image processing like Photoshop, that might be a kind of a dumb way to go. It would work. You'd still recognize the image, but it's going to be as smooth as, say, averaging. But for neural nets, that max value is very often good at detecting where the most interesting activity is, where that convolution found the greatest probability of having an edge or some object. So max pooling is simple, but turns out to be very effective. So now we have all the pieces we need to build a real convolutional network. We've got an input image. We apply these convolutions to it, and once in a while, we decided we want to, before we apply some more convolutions to it, we want to zoom out to get higher level detail so we can do a pooling operation, max pooling here. And then maybe we apply some more convolutions to it. And then finally, when we're done and we think we've done a good job at detecting all of the content and pieces in this image, we invariably finish up with a fully connected layer, just a normal, fully connected, all the neurons talk to all the neurons layer, because that allows us to have a lot of more abstract reasoning and push out a result which hopefully assembles all the information that these convolutions have squeezed out of the image. So here's what an actual real, very effective network looks like. As a matter of fact, this network right here was one that really convinced people that deep learning, this approach, is the superior way to do image processing. Up until this point in time, it was still very much a race between deep learning neural net approach and lots of classical machine learning approaches to do image recognition. After AlexNet, which is this, came out, people recognized that deep learning is very powerful in approaching image recognition problems. And this was only 2012, not that long ago, that people really embraced the idea that deep learning might be a superior way to go after image recognition issues. So here's AlexNet, and it introduced a couple of concepts. It also introduced really aggressive use of this rectified linear activation function that we looked at last week, and we're going to use in all of our networks here. Up until then, people were still largely favoring smoother activation functions that we looked at. This network also didn't introduce, but made effective use of 11 by 11 kernels. So the convolutional kernels here aren't 3 by 3, they're 11 by 11. And the first layer, for example, had 96 of them. So the first layer, we throw the image, this is the schematic of it down below, and you can see there are a lot of pieces here. But the first layer that takes the input image then applies 96 different convolutional filters to that first layer. Each one's 11 by 11 to start to find stuff. Like I was saying, lines or edges, vertical lines or diagonal lines, to find pieces of the image that the next layer can then start to assemble into higher level objects. So this is the first layer right here. And if we look at the schematic right here, you'll see a bunch of numbers in here if you squint hard enough to see that there are 96 11 by 11 kernels here. Other layers have differing numbers of kernels in different sizes. And the full network looks like this, but it's all made up of the same pieces. The same basic pieces. Now, it's very important for me to emphasize right here that when I've been talking so far about the things these kernels learn, I've been saying things like edge detection, but it is not the classical hand-assembled kernels that prior to deep learning were used for image processing, where somebody did take and recognize through analytical means, painstaking manual methods, that this filter can learn to recognize edges, like we saw with that picture of the rabbit earlier. Instead, what we have with deep learning are filters that learn themselves. The convolutional filters are a bunch of weights, the weights that make up the filter. They get adjusted and tweaked as we're learning imagery, as they're learning to recognize images. And so in AlexNet, when AlexNet was done learning, the first layer filters, the 96 first layer filters, looked like this. And if we look at any one of these, it is not possible to say this is an edge detector. This detects horizontal lines. Instead, what we find in deep learning are the convolutions end up learning abstract things that to us as humans don't make, they're not something that we can directly explain precisely what they're doing. It's only in aggregate that they start to work effectively. So the filters that you're going to find at any layer in a deep learning network are not, hey, here's a filter that recognizes eyeballs. It's that they recognize a bunch of abstract pieces, and in conjunction with each other, they're effective at ultimately recognizing an eyeball. But they do not end up learning things that are as simple. You can't point a finger at this and say, this recognizes vertical lines. Sometimes you can kind of get in the ballpark of what they're doing, and there's great interest in having better understanding of the things that they are learning and guiding it, because sometimes pulling that information out allows you to generate things that are useful. But in general, the convolutions that the network learns are not going to be simple, this recognizes vertical lines, this is horizontal lines, this is circles. That's not the way these things work. Okay, let's look at using these pieces to build a much more accurate character recognition program. Here's the full program. I'm just showing it to you up front so you can see that as we step through it, that it's not an endless process. So fear not as we start to step through this line by line. There aren't hundreds of lines here. Here's the full MNIST code to implement a multi-layer convolutional network with dropout and max pooling. So it's going to have a lot of fancy features. It's going to be much more effective at recognizing things, but it's not that large and complex of a program. As a matter of fact, you can, if you just quickly look at this, you could see that half of this code is stuff from our previous example from last week. Basically, your boilerplate code for TensorFlow to train things and to read some variables in. But we'll step through this line by line as we build our network here. But here's the full network. So let's start at the top. Well, this looks to begin with like what we did last week with our basic MNIST, our prototype, not even quite neural net network, which is that we load the TensorFlow framework in, read some MNIST data in as placeholders here. So our placeholders, once again, you may recall, are the inputs and outputs as far as TensorFlow is concerned. So in our case, the input's going to be the image. The output is going to be the label, the one that we're generating that we hope is correct versus the label that we're given that we're told is the correct digit. And so that's what the placeholders are for. However, what's going to be different this time is that last time we just took our 728 pixels and stretched them out, or 746, whatever it is, stretched them out into one big vector and threw that at the input layer of our network. Now with convolutions, we're going to keep that two-dimensional shape. So we are going to retain a 28 by 28 shape of these things and apply the convolutions to that array, that two-dimensional array of pixels. And once again, I hope that most of you intuitively think that makes a lot of sense. We were throwing out information before, and we're keeping it this time. So to keep it, we make sure that our input vector has this 28 by 28 shape. So that's what we've got right here. So we've got this 28 by 28 image. And now we're going to use our first convolutional layer. This is the full layer right here. We'll step through the pieces of it to analyze that image. So the first thing we have is the convolutional filter weights. And we get to pick both the size and the number of filters in this first layer. In this case, we're going to have 5 by 5 convolutional filters, and we're going to have 32 of them. And so the obvious question is, where did you get those numbers from? And the answer is that you look at other similar problems. You say, okay, somebody else looking at, say, grayscale images that are low resolution out there, they might only need 5 by 5 filters for these small images because the images are only 28 by 28. So 5 by 5 filter might be good. And how many things should we look for in this first layer? Well, I've looked at some other things where people are looking at crude image recognition, and 32 filters on the first layer seems to work. I mean, that's as detailed as your thoughts are going to get. You're basically just grasping at the nearest problem you can find, using those hyperparameters to get you off the ground. But then due diligence says you should begin to explore and see that I should change this. I should try to go for 4 by 4 filters or 3 by 3 and see if they still work. Because smaller filters will be a lot faster to train, so I can train more cycles. So you don't want to be wasteful. But by the same token, that might not work so well. It might not be enough weights to learn things properly. So I should experiment a little bit with this, but we're going to start with 32 5 by 5 filters. With neural nets, you need to initialize the values to something besides 0. With our really simple approach we took last week, we didn't worry about this so much. We could just let TensorFlow do its default 0 initialization. With neural nets, though, in general, you can't initialize things to 0 because if everything's 0, first of all, you don't have any gradients, you don't have any differences or anything which the solver likes. But more importantly, if things are 0 or even the same number across all the neurons you start to train, well, 2 neighboring neurons that's set with the same value that are looking at the same pixels are going to learn the same thing, and they're going to be adjusted by the solver the same way. In other words, they're going to be lockstep synchronized with each other. Separate neurons in your layer aren't going to learn different things. So to get them off the ground and learning different things, we need to initialize all the neurons in that layer to different values. And TensorFlow makes it very easy for us to do that by basically we can just specify for the initialization a standard deviation. And so we can just pick it. By the way, it's also another hyperparameter. What standard deviation should you pick? And the answer turns out to be, for most neural networks, if you've got activation functions that look kind of like the ones we're using, standard deviation of 0.1. We want small values is probably a good way to go. So TensorFlow makes it very easy to make sure that our initial weights are all initialized then to some random values with an appropriate standard deviation. So these are our weights. We also have biases for our filters. And our biases should be initialized. Biases can be initialized a little bit more simplistically. We're just going to initialize all of our biases to 0.1 to start with, and that'll work just fine. So we have our weights and our biases all initialized for our first layer, which is, again, 32 of these 5 by 5 kernels. Okay, now we've got things initialized. Let's actually, and we've got them defined, let's actually tell TensorFlow what we want to do with these kernels. And what we want to do is 2D convolutions, the kind of convolutions we're looking at, 2D convolutions with our input image. TensorFlow has this built into the toolbox. 2D convolutions are, of course, very important. So it's built into the functions that we have available to us. And we pointed at the input values that we want. So the image, we tell it what the weights are of our kernels. We tell it what the stride is that we want the convolution to do over the image. In our case, we're going to use a stride of 1. We've got a small image, so we're just going to step 1 pixel at a time through it. We had larger images. You might want larger strides to shrink things down. Well, at any rate, we picked a stride of 1. It's another hyperparameter. TensorFlow takes care of the padding for us. That's a nice feature that it has. So in other words, same just says, hey, don't do any fancy, don't keep the same size image from one convolution to the next, just pad it out with zeros. So this is our 2D convolution. When we're done, we want to add the bias to it, and then we want to add our nonlinear activation function. Because once again, the nonlinear activation function is what makes this thing a neural net. Convolutions are just linear functions. They're just multiplies and adds. So convolutions can do a lot of nifty things, but what they can't do, if you think back to last week, when we said the convolution, the nonlinear activation function is what allows that rubber sheet of data that our data is on, where we're learning things, to really warp instead of just scaling it or bending it, the warp ability that the nonlinear functions gave us that we saw with those animations last week, that warping ability shows up here when we finally apply this rectified linear activation function to it. So until we did this, we're still only have linear operations. As fancy as convolutions are, they're just linear. So it's important to add this piece into the mix to give us that additional capability. And so now we've got right here the full definition of a layer that has 2D convolution with a bias and then a nonlinear activation function applied to it. So now TensorFlow knows what to apply to this layer. And so in our case, we're also going to intentionally shrink that down. We're going to zoom out on these digits so that we can get some higher level information. So we're going to use a pull operation before we pass it to the next layer. So TensorFlow in the toolbox has pooling built into it, different types of pooling. We're going to use max pooling. So it has max pooling built into it. And all we need to do is point the image, the now convoluted image, to the max pooling function. And the pooling operation also has a stride to it, but we're just basically going to pull down by a factor of 2 here, and it'll pull for us. So at this point, we've defined our entire first layer right here, and this is typical of a layer in a real serious leading edge application trying to do anything from image processing to learning to play Go or chess, where you're applying convolutions to your data. You're pooling it at the end to shrink down before you go on to your next layer. And so we've implemented the whole layer. To do the next layer looks a whole lot like the same stuff, except we can choose some slightly different hyperparameters for this layer, although it's, again, very similar. So we're going from this layer here. By the time we pass it on to the next layer, we're down to a 14 by 14 pixel image, because we've given a 28 by 28 pixel image. We did our max pooling here of 2 by 2. So we've shrunk it down by a factor of 2. So now we're 14 by 14 pixels going into our next layer. Our next layer, we've got these 5 by 5 kernels again, but this time I'm going to decide we want 64 kernels in this layer to look at things. Why 64? Well, I think that we've learned stuff about the first layer, edges and boundaries and things like that. At this next level, maybe, I think there's a whole lot more to learn about the orientation of all of those things together. What makes a 0 different than an 8 is that little piece in the middle. And so we'll do a whole lot of more, well, not a whole lot more. We'll do some slightly more sophisticated analysis on this second layer right here. Well, again, it's a hyperparameter that we're free to choose. I've choose 64. You may very much want to experiment and see what would happen if we did 32. 32 kernels would train faster, but it might be dumber in some sense. We could go to 128 kernels. That would be smarter, but it would have a lot more weights and train a lot slower and take more memory up in our GPU. So this is a hyperparameter that we've chosen, but it ends up working. We'll see when we're done here. So we now have, in our second layer, we've got 64 kernels that are 5 by 5. And coming into it, we have 32 kernels from the previous layer. So we need to have this many weights. We once again have biases for each of our 64 kernels, and we apply the same 2D convolution operation. We add our bias to it, apply the rectilinear nonlinear function to it, and do pooling once again so that we can get down to a 7 by 7 image. So we've got a good example right here, a typical example of succeeding layers of a convolutional neural net that go from the input 28 by 28 image down to a 14 by 14 image, and finally, when we're done here, we're down to a 7 by 7 image. And each of these kernels along the way are hopefully extracting out useful information for us to know. We've decided now, we've made the architectural decision, I've made the decision that that's all we need for this MNIST problem, is a couple convolutional layers will be sufficient. And so now it's time to go to that fully connected layer at the end, which finally squeezes out, hey, what are the real, the digits here, how to put all these convolutional pieces together to get the digits. So our fully connected layer here at the end is going to be, by my choice, it's going to have 1024 neurons. I've decided that's how smart I want this layer to be, is 1024 neurons. So once I've picked that, then the rest of the math follows from what's being fed into it. I'm being given a 7 by 7 image with 64 different kernels giving me outputs. 60, when I say kernels, and that means convolutional, so kernels, I hope you're getting the idea now as I keep switching terminology up, that kernels, filters, that's the name for the convolutional filters. They can be called kernels or filters. So we've got 64 of these convolutional outputs coming to us in form of 7 by 7 images, since we've zoomed out that far, and I've chosen 1024 neurons, so that tells me how many weights I have to have going into this layer right here. Once again, I need 1024 biases then. And at this point, I am ready to feed this into my final layer, except that since I'm going from these convolutions, these 2D images, and we're going to a normal layer, fully connected network layer, I need now finally to unstretch, to take the 2D image and stretch it out into one big vector to feed into that final layer. So just like last week with the MNIST thing, we were always working with one big vector. When we get to a fully connected layer, we do need to stretch things out to one big vector. So it's time to do that here. It's time to take all of the things that the convolutional layers have learned by looking at a 2D image and stretch it out to one big vector to throw it at a fully connected layer. So that's what this final reshape thing does here. It reshapes our 7x7 images into a big string, a big vector that can feed into this 1024 neural net. So we do that. And now it is time to for that neural net to learn enough to pass along the final output to the final layer, which is going to be 10x10 output layer. So the final layer, excuse me, a 10, not a 10x10. The final output layer is 10 neurons that are 10 output neurons. So we go from our 1024 neurons, which are our final layer, which is got all the smarts in it, to our 10 output neurons, because we want one of those 10 neurons to light up and tell us whether it's digit 0 or 1 or 2. And so we have 10 output neurons. That's handed to us by the problem that we've given ourselves. So our final layer of weights is going to be 1024 by 10. So here's our output layer right here. It's going to have, once again, weights and biases like every other layer had, but we're going to introduce a new thing, a new capability here, the last piece of the puzzle, and that is some way of preventing this neural net from overfitting the problem. And so this is a term that I just mentioned probably very briefly last week, but it's important to dive into now, which is that overfitting is when you take your training data. Last week I said we had training data and test data, and it's important to keep the two separate. And the reason I said was to avoid this overfitting problem where we get really good at looking at the training data, but we get so good at looking at the training data that we're not really good at learning about new data that we see in the future when the thing goes out into the real world and is supposed to recognize new digits that weren't in our training set. And getting too good at your training data, memorizing your training data so much that you're not good at generalizing to new data is called overfitting. And all neural networks are susceptible to this. It's a major problem. You might think that's a minor problem. No, it's a major problem. It is the number one issue to avoid when you're training a neural net, especially because today's neural networks have so many weights in them. When you start building a modern neural network, you find yourself with enough layers that are big enough that they have enough weights. That many weights makes them very susceptible to being able to just memorize the training data and not really learning about the training, not being able to generalize from the training data. So overfitting our data makes us in danger of not being able to generalize to new data that's not in our training set. And the way we test against that is we keep a piece of our data set aside as test data. We don't train it. It's not used to adjust the weights of our neural net, but it is used periodically to check and see how smart our neural net is at looking at that data that it hasn't trained on. And if we graph as we're going along here, as we're training, we can see this overfitting begin to happen. And this indeed is the way that you monitor this in most cases. So here is our training accuracy as we're running this thing through its iterations here when we're done. And this is the same thing we did with MNIST last week. We ran through a bunch of iterations here, however many epochs you go through here, however many mini batches you're training through. As you go through, you can track the accuracy. And in this case, the accuracy of our neural network is going up and up and up. And that's great. And we're very happy with ourselves as it's doing that. And we think we're up to here. We're up to 98% accuracy or whatever we are up here. We're very pleased. However, if we look at what happens when we periodically look at the test data is the data that's never used to adjust the weights. It's just used to verify what's happening. The testing accuracy keeps going up as well. That's great. We think this net's learning how to really look at digits. But at some point here, around here, we can see that the training accuracy keeps going up, but the testing accuracy doesn't. Matter of fact, it even dips a little bit here. This is the visual way of seeing overfitting at work happening. We are seeing right here where the network is getting good at memorizing the training digits, but it's not really learning how to recognize digits any better. And so when we look at the test digits that aren't used in the training, it's not doing better. So this is overfitting right here. So how do we prevent overfitting? Well, the ways to prevent overfitting are techniques that are called regularization, and it's a whole handful and growing handful of techniques that help to prevent this from occurring. The one we're going to use is one that sounds very crude, but is incredibly effective, and it's become widely adopted, which is called dropout. What we're going to do is, while we're training our network, we're going to take half of the neurons in our final neural net layer as we're training our network and rip them out. We're going to intentionally brain damage our neural network as it's training. And this dropout technique, where we just drop out half the neurons as it's training, does actually turn out to be very effective at preventing overfitting. If it might not seem obvious why that happens, well, it's not obvious. This is one of those things where it's very exemplary of where neural nets, where deep learning lives today, which is that techniques which people didn't even consider, well, didn't even exist not long ago, turn out to be really effective, become widely adopted. So dropout's commonly used in many, many different architectures these days. And yet analytically, it's very hard to get a handle on. So you can make some justifications for it. You can look at this as, by removing some of the nets, the neurons, you're really training an ensemble of things. There's lots of different ways you can consider why it makes sense. So it's not a complete mystery, and it's not like people, I mean, obviously there's a reason that somebody was inspired to do this in the first place, which is to disrupt this overfitting mechanism. But to look at this analytically is very difficult to do, to look at it precisely in any kind of method where you're trying to figure out what the real convergence of this would be. But this dropout technique turns out to be really useful at preventing overfitting, so we're going to adopt it here. And once again, TensorFlow makes it very easy for us to drop this piece in. It's part of the toolbox. And so what we're going to do on our final layer here is we're going to add in dropout. And all we need to do is specify, hey, drop out these weights here with a keep probability. So this keep probability parameter here is how many are we going to keep? And in our case, we're going to drop out fully 50% of them. We're going to find that parameter shows up down below when we start training, so it's not stuck in here yet, but there's going to be 50%. So we're going to only keep 50% of our neurons as we're training here. And that might seem like you're missing an awful lot of neurons there, and indeed that is the case, but it turns out to be effective. So this is our final layer here, which now has 1024 neurons going down to our 10 output neurons, has dropout included in here, and finally spits out at the end of all of this here our actual predicted value. And the mechanics, remember, of a fully connected neural layer are as simple as it's a matrix multiply plus this bias function, and that's all there is to it. So, okay, let's look at running this thing, actually forcing it to run right now is a matter of just telling TensorFlow what error we want, just like last week. How do we define our error? And we're going to use the very same definition for error that we had last week, which is the softmax cross entropy with logits. And I hope you all recall that. That's a pretty nice, straightforward way to specify an error whenever you're doing categorization, whenever you're saying, is this one of this category? Is it cat or dog? In our case, is it digit 1 or digit 3? And if you're digit 1 and you guess digit 5, how much error should you have? Well, we saw last week why softmax cross entropy works pretty well. So that's the error we're going to define. Our optimizer, last week we used stochastic gradient descent, which is standard gradient descent optimizer. We said that's a classic way to go. But this week, why don't we try, just because it's a newer thing which has some benefits too, why don't we try a different optimizer? Because TensorFlow makes it as easy for us to grab a new optimizer as just say, hey, which ones are in the toolbox? And we'll find that the atom optimizer is a newer and more popular tweak on gradient descent. It basically uses some momentum that I discussed last week when you're finding minimums in a function, and it uses an adaptive time step. So we're going to try it because, hey, why not? It's easy to do. So where we had gradient descent last week, we're going to stick in atom optimizer. Atom optimizer has an initial step size. That's the only parameter we need to specify for it. So I've swapped in atom optimizer as our solver. At this point in time, we've now given TensorFlow a complete graphical description. I say graph because TensorFlow thinks of things in terms of a graph, to get from our input here, x, all the way down to our output right here to get our final value. So we've got our input to our final value right here. We've got our error defined right here. We've got our optimizer defined. And now let's make some predictions here. And we can say a correct prediction is where the maximum value of the output equals the correct value given to us by the MNIST labels. So our accuracy then will just be, we'll take the mean of all these predictions here and see how accurate we are. So if we run this with the same procedure we used last week, basically start an interactive session, and then we're going to run this thing here 20,000 time steps, 20,000 batches of 50 here is what we're going to do. So we're going to run this 20,000 batches of 50 to get our results. Along the way, though, we're going to spit out some interim accuracy as it's training, as it's going. With our simple one last week, we just spit out the final accuracy. With this one, we're going to spit out some accuracies as it goes. However, when we do spit out those accuracies, we want to make sure, first of all, that we compare it against the testing data. So you'll notice when it stops periodically every 100 time steps to print out its accuracy, it does two things. One of which is it uses the test data, not the training data, and the other one of which is it now turns the keep probability, this dropout, it turns the dropout off. It basically says keep all the neurons. When you want to see what your final result is, you turn all the neurons back on. Don't be confused. Dropout is only used during training to prevent overfitting. Your final network has all the neurons fully connected. So when you're finally done and you want to recognize characters or have a self-driving car or whatever, you use all the neurons. So when we test to see how it works, we turn all the neurons back on by turning the keep probability up to 1 here on a dropout layer. So we test every 100 iterations as we go. And what we will find now is that this network now tests to be 99% plus accurate. And so what we've done here is we've used multiple layers of convolutions with some pooling in order to zoom out. And on the final layer here, we've used some dropout. We put all these pieces together and we get some much, much better accuracy. As a matter of fact, this is about human level of accuracy on MNIST. And these pieces right here, I'll show you some examples of, are the pieces that are commonly used in much more complex networks that do absolute leading edge, state-of-the-art self-driving in cars, or Go, or chess, or many, many problems that use convolutions. So you now, I hope, understand, and you should ask questions if you do not, I hope understand the most important building block by far in current deep learning architectures. This next demo I'm going to show you, and I'm always reluctant with real-time demos here, but this one is so good that I can't help myself. This demo I'm about to show you will emphasize exactly what we've been doing, and several aspects of it, actually. So let me fire it up here and show you. And you are all welcome, and you should all go and play with this. Here we go. You should all go ahead and play with this demo. So what we have right here is a very similar, not exactly the same network, it's just enough different to be interesting, but it's a very similar network to what we just did to recognize digits. So the way this works, and this works in real time, what you're seeing here is a real-time thing being run on a web server out there, is I'm going to draw a digit here. I'm going to try to draw, excuse me, I'm using an awkward mouse. I'm going to try to draw the digit 2, and it in real time recognizes indeed that this is the digit 2. Its first guess is 2. And here, this is what makes this a really nice demo. Over here on the side, we can actually see the pieces of this network, the architecture in action. So we have a number of layers here. We have an input layer, which is 2, where I just drew in the digit. We have the first layer, which is a convolutional layer. And it has 6 filters. So if we look at the 6 filters on this convolutional layer, we can pick any given pixel, and you can see it's showing us where it derived those pixel values from. This is where that convolution was scanning. This pixel for this convolution output right here was scanned from this part of the image down here. So you can see as you move over the convolutions exactly where it derived the pixels from. And we can see the 6 convolutional filters in this first layer. And if we look at those 6 filters and you peer at them, you might try to figure out what are they learning. And if you look at them, you will not find that one of them is an edge detector. But on the other hand, if I look at this, I can see, yeah, they kind of are interested in edges. That makes kind of sense that the first layer of convolutions, they kind of do figure out some edges here. They are interested in the boundaries. And that only makes sense if we're looking at images. So I can see that they're kind of learning some things. Maybe this one looks like it really cares about upper and lower edges a little bit more. But you're not going to be able to figure out exactly what these filters do in some precise method, for some precise definition. The next layer here is a pooling layer. Called a downsampling layer here, and it pulls things down to half the resolution. And so you can see where it gets its pixels from. It's not so interesting. It just basically collapses things down. The next layer here is another convolutional layer, and you can see where it's drawing its information from. On the other hand, it is even more abstract as to what this layer is learning about the image. You will have great difficulty figuring that out. Then it pulls down one more time. And then we have, on the end of this one, we have two convolutional layers. So if we look at this pixel right here, this neuron right here, we can see where it's getting its inputs from. And then we have one final convolutional, fully connected layer here. So we have two really smart convolutional layers in this architecture. So we have a very similar, but again, different enough to be interesting architecture to what we did. We have two convolutional layers, each with downsampling, and we have two fully connected layers at the end, and you can play with this and see what it does. So let me draw one more digit here. Let me draw the number, I'll try to draw a 3. Come on, mouse. And there's a 3, and indeed it guessed that it was a 3 and not a 7. So you can see this in action. And I encourage you to investigate and play around with this to really reinforce the concepts that we covered here today. In particular, the fact that these filters are not spitting out really simple, easy to digest things, but they're very effective at doing what they do. Another concept that's really wonderfully reinforced by this demo is that this is running on a web server, some generic web server somewhere, somebody's personal web server. It's not the guy that did this is, when I first stumbled across this demo, I was really impressed with it. Adam Harley did it, and he was in Canada at the time. And by the time I found this, he had migrated here to Carnegie Mellon right across campus from me. So he's running this currently on his personal web server he left behind up there. And the thing works almost instantaneously to recognize digits. And that illustrates that once you train the network, the forward part or the inference part of the network is very, very cheap and fast. So once this thing, to train this thing might have taken tens of minutes to do potentially on a decent GPU. But once it was done, it could be put on a generic web server without a GPU, and it runs in JavaScript. JavaScript is far from an optimal high-performance language. It runs in JavaScript, and it works almost instantaneously. And that's because once you've trained and found the weights, the inference or forward part of this network is very fast. As we can see, it's just a bunch of multiplies and add functions, basically, with a little nonlinear function mixed in there. That's the kind of thing that is easy to make hardware do. GPUs are phenomenal at it. That's why they're typically used for this kind of training. So the inference part is very fast. And that is why these things are so useful in the real world once they're trained without massive amounts of hardware. Here it is. Let me see if it runs when I click on it. Yes. Here's an iPhone demo, for example. There's a recognition. This does recognition of people, different objects, bicycle in real time, puts bounding boxes on them, as a matter of fact. This runs in real time on your phone. And that gives you some idea. Training this took a lot longer. You never want to train something like this on your phone. But once you found all the magic weights, actually running this is something that works in real time here. You can see in milliseconds, it's able to analyze these images, again, in real-time video on a phone. That is why things like self-driving cars are possible with consumer-level electronics. As a matter of fact, for those of you that are interested, the demo day that Tesla puts on, they have their, I can't remember the name of it now, but I think it's going to be a recurring annual event, but they had their first one this year, which is their AI day, where they put together a presentation about an hour and a half long, which you can find online, on where they stand with their technology and their self-driving cars. And if you look at what they're putting into cars right now, all Teslas now have these devices in them, which are really, really good at doing inference, doing vision recognition. They're trained elsewhere. They're trained on some data center-sized capability back at Tesla HQ, but in your car, you have, and again, this is every production car that's coming off the line right now, you have this processor in it, which is really, really good at doing matrix multiplies, basically. Here's the actual hardware. Here's the layout that they showed in their presentation. Oops, I don't have my laser pointer turned on. Here's the actual hardware. Here's a picture of the chip that's sitting in every car, and it does pretty much 96 by 96 multiply adds. That's what it specializes in. It also has some special hardware in there to do this rectified linear activation function and some pooling hardware. So you now, from just what we've learned here in the past week, can see, can understand the pieces of hardware that make up a very interesting piece of current technology, leading edge technology. It's pretty much just good at the operations you've learned here this week. So I hope that convinces you that you haven't learned a tiny slice of what goes on out there in the world. You've learned actually an enormous amount of the landscape in deep learning. This thing is capable of doing about 72 trillion of these operations per second. And that's how it's so good at being able to recognize the many, many things that it must recognize in real time as it's driving a car around. Okay. This is so important, this idea that inference is simple, bunch of simple math operations, that everybody is now getting into specialized hardware. So you've got NVIDIA with their GPUs, and their GPUs these days even have the good ones like we have on Bridges, like you've been using, have very dedicated hardware just to do low precision matrix multiplies. One of the things we haven't talked about yet is that the mathematics required for this is actually quite low precision. People started out doing this with thinking 32-bit precision, which is kind of the middle of the road in scientific computing. And then they realized that they were getting equally good results, but much faster with 16-bit precision. And currently, the world is working with 4-bit precision in an awful lot of deep learning problems. 4 bits is not a whole lot of precision, right? That's a very, very inaccurate representation of a floating point number, but it turns out that that is sufficient to do, in many cases, to do deep learning. And the less precision you have, it means the faster you can do it, the less memory you need for your weights and whatnot. So current NVIDIA chips have very good mixed precision, meaning they can do 16 and 32-bit mixed precision calculations with 4x4 matrix multiplies. They've got a lot of the hardware on the board just dedicated to just those simple operations. Google's tensor processing units, for example, can do 420 teraflops of just these kind of simple operations, and they've got data centers full of these things. So that's where, when you talk to your personal assistant, and all the many types of deep learning, from the voice recognition to the language processing to the other things that go on, they're driven by warehouses full of this kind of hardware. Intel is now dedicating special types of operations, even on their standard chips, to doing these lower precision matrix multiply type of operations. So the new vector instruction set, they've had vector instructions for doing math on their processors for decades now, but the new vector instruction set has now 8-bit multiplies in it, which, to anybody that follows actual scientific computing, 8-bit multiply sounds like we're stuck back in 1970 here, and yet it is the absolute bleeding edge of the newest Intel processors. There are attempts to make hardware that even looks like a neural net down at the lowest level, so it doesn't actually even have to do fetching things from memory and doing multiplies and registers. Instead, it's laid out like your neurons are connected. That's called neuromorphic computing. IBM has been a leader in that for a good while. And the inspiration for that, by the way, for neuromorphic computing is that your human brain, which is certainly an effective neural net, only uses 20 watts of power. And yet, to simulate the human brain's neural net capabilities these days is something that requires an exaflop level computer, or in other words, a computer that requires well over 20 megawatts. The first ones will be built in the next couple of years. Next year or so, they'll be bringing them online. And those machines are all over 20 megawatts of power. So the fact that it takes over 20 megawatts of power to simulate a human brain, which runs about 20 watts, gives us the idea that there's lots of room for improvement in the actual implementation of these algorithms and the electronics behind them. Your human brain is analog. It does lots of pruning. So where the weights fall to a low level, you can just turn them off completely. There's lots of opportunity there to keep improving things, given our inspiration from Mother Nature. As I pointed out last week, 2 sources of inspiration here. We've got the algorithmic one. We keep improving our just algorithmics from a mathematical perspective. But Mother Nature continues to provide a lot of inspiration for how to improve these things as we go along. Okay, let me point out again that with these convolutional nets, we go from low-level detail to layers that assemble things into higher levels of content. And you can see these things very visually in the popular online applications like Deep Dream Generator, which allow you to feed it a couple of images and say, use this one for the content of the image and use this one for the style. And it basically collides these things in a neural net. So it goes in a neural net and it uses one of them to generate the style, in this case these die, and the other one to generate the content, in which case is a picture of a cat in some foliage, and you end up with a very, very dramatic visual demonstration of how the nets are learning different things at different levels. Here's another one from Deep Generator, of photograph of of a touristy site combined with the style from your favorite painter, and you can end up with your photograph being done in this style. So I hope that gives you an idea. Here's photograph versus comic book type art, and you end up with this photograph in this style. So you can get the idea that the different levels of the network, the different convolutional layers, are absolutely learning style, low-level stuff, versus content, how the high-level pieces fit together. Okay, there are some tools here to allow you to do this stuff as you get more advanced. So I hope that many of you will go and feel emboldened, and our exercise will encourage you to go ahead and start doing this stuff. Play with the exercises, go ahead and start to think about applying it to your own applications. As you do that, you will find yourself wanting maybe more sophisticated tools and support. And one of the reasons I chose TensorFlow is the framework. It has a wonderful ecosystem of tools to allow you to do things, one of which is TensorBoard, for example. So TensorBoard, if we pull up our MNIST network, it will show us, first of all, it will show us actually, here's the graph that TensorFlow thinks of our MNIST network as. So here's the graph from input to output. But why you want to use it in general is to understand the variables, things are running in real time, and we can see different variables in real time and how they're changing. If you start deciding, how many filters do I need, how much activity is going on in different areas. So there are ways to begin to pry out the inner workings of the networks as they go. TensorBoard is one convenient piece to do that. Again, there's a big ecosystem built up around TensorFlow. It's one of the reasons I chose it. Most important thing, though, for example, is just to see the accuracy on the output side. Here we can see our accuracy as we train our network, and we can see it in action. But we can also period any of the smaller variables that we want to along the way. Okay, the final exercise here that I'll leave you with is once again to think about the hyperparameters, only this time it's a much richer problem than it was last week, because we have plenty of hyperparameters in the network that we just built. And so I've mentioned them as we've gone along, but there are plenty of them. So we can have a friendly competition here for any of you that want to participate. You can, and to make it easy so that people don't go too far down the rabbit hole, I'm going to say that for our purposes of our competition, although you can certainly explore things any way you want, but for purposes of our competition, which single parameter change can you pick that's going to have the greatest effect in improving our accuracy? Or which single parameter change is going to improve our efficiency, or in other words, how fast the thing trains the best. So, and again, it's a combination of these that's obviously going to be most effective. We have so many parameters to play with, but that's it. That would be an endless problem. So instead, if anybody that wants to investigate things this way, if you send me your results, then for all of you that participate, I will send the answers back out and let everybody know who won. So please let me know if you don't want people to know who you are or whatever, but otherwise I will let everybody that participates let who the winner is and what they found to be most effective at improving this problem. So that's a good final exercise. It's very approachable, I think, with what you know right now. I hope the environment that you're working on, Bridges, is very friendly and allowing you to experiment with this stuff pretty quickly. That's important if you want to be productive in this stuff, because hyperparameters, once again, are where all the effort goes. Okay, with that, we've reached the end of our actual lecture. And as per last week, I will answer questions and or help people that want to play in real time with the exercises till I think we have another 20 minutes scheduled here, and perhaps longer than that if nobody kicks me off the air. So I'll open the floor to questions and or hang out to just support you if you want to start to play around with this exercise or any permutations thereof. And for those of you that want to wander off now, I thank you for your time and attention here, and I hope this turns out to be useful to you. And if it does, I'm always delighted to hear back from researchers who have actually been able to turn this into something interesting for their own purposes. So please drop me a line and let me know if it's been helpful.
All right, thank you very much, John. We do have a couple questions that people have sent. So the first one is, how do you ensure that each respective filter learns different aspects and features of the input image with regards to each other?
That's an excellent question. How do we ensure that each filter learns different things? And the answer is that is where the random initialization is the only tool you have to do that, and you hope that it's effective. So by randomly initializing the filters to start with, we hope that that sends them off in different random directions to start to learn things. And that turns out to be, in general, effective. But it's that simple, really. It's just because they're all initialized with random values. And so I always like to pull up a picture to emphasize things. So let me pull up the Kravitsky's here. So these filters here, for example, in AlexNet, the only difference for them starting, they were all started exactly the same basis, except they were all just randomly initialized to different values, and that's what set them on a slightly different path and eventually ended up with them learning very different things. But it's just a random initialization. That is the only tool you have to do that.
And it looks like this question is related to the exercise. For measuring time efficiency, what functions can be used in TensorFlow?
TensorFlow actually has timer in it, but I would suggest for your purposes that you just when you're actually running the thing, just put either time in front of the command. Yeah, that's probably the simplest way to do it. Is just put time in front of the command. You can put timing functions in. And TensorBoard, by the way, has timing things, and there's also a perform. So if you were serious about this, let me give you the right answer for this is that there is a performance profiler for TensorFlow. So when you get serious about doing production and you really care about timing, because now it's going to take 1 million hours to train your network, and so if you can shave 20% off that, you're saving yourself a lot of time and money in most cases. So there is an actual real timing tool for TensorFlow. Its name's escaping me at the moment, but well, why don't I go and dig that up while I'm talking. But for purposes of the exercise, I would suggest just putting the time command over when you actually run the thing. Here, let me bear with me. I've got here we go. When I have the luxury of more time, I have a greatly expanded version of this talk, but it is a 3-hour talk instead of this, and consequently, I have the ability to dive into the tools a lot more. And here is here we go. So here is the tool. Yes, it is the built-in tensor graph tool. So if you're serious about this kind of stuff, and I hope many of you become serious, there is a very simple and easy to use tool for doing timing that's built in. If you import timeline in here, this will spit out, just adding in a couple lines, just adding in a slightly different session command right here, allows TensorFlow to output a lot of performance information, and it then spits out a file. It's a JSON file actually, but you need to analyze it in Chrome. It is, this is where TensorFlow's association with Google shows up. The Chrome browser is the only one that can really look at this file then. But if you load this file into Chrome, you get a very, very nice output of your performance and where things are going. So again, for purposes of the exercise, just use time. For purposes of your own performance monitoring in the future, there are a variety of tools, but this is by far is the number one I recommend for people to dive into and get a handle on things when they come to me with a serious application that's taking a lot of time. There are lots of tools in the TensorFlow world, but this one's very lightweight. It's easy to do, and it gives you a lot of detailed information.
That was all the questions in the chat, so we can go ahead and open it up. If anyone has questions about the exercise or anything, feel free to unmute yourself and ask it. It's probably a little easier to explain your question than trying to type it out.
Speaking of exercises, I will take this opportunity then, if nobody has a question, to point out that if you want more complex exercises, the incredibly wonderful thing about machine learning and deep learning in particular is because it's driven by these standard benchmark competitive types of things, that there's a nice evolution from the MNIST network that we did. You could go to the CFAR data set, which is out there, which is 60,032 by 32 color images with 10 classes in it. And that doesn't take much more than what we've done network-wise to be effective. Then ImageNet, which is what that AlexNet program I showed you actually does. It's 150,000 photographs. They're hand labeled with 1,000 different objects. So this is a really pretty serious image recognition problem. Is available out there at this website as a data set. And lastly, if you want to go off in a different direction, there is a website which kaggle.com, which consolidates pretty much all of the data sets that are out there. It actually runs competitions. They've got over 20,000 data sets in vastly different areas. So, I mean, everything from botany to criminology, public health, all kinds of stuff. They're really all over the place. And they run competitions too. So, for example, right now, or when I made this slide a month ago, there was a steel defect detection competition with a $120,000 prize out there. They have a bunch of things which are competitive. And also, by the way, here's MNIST. No prize for MNIST these days, but if you want to compete with improving the MNIST data recognition thing, there's a competition running right now. So if you want exercises beyond what I've given you, there's a bottomless well of wonderful exercises with data sets of people competing out there, and you can see their solutions. It's incredibly exciting for people that want to continue to pursue this stuff, to be able to find an exercise that really relates to your own area or your own enthusiasms.
So someone just posted the question, when I input the line of code 1_hot equals true, I get an error that says IO error, error no socket error, network is unreachable.
Well, it's hard for me that's kind of really out of context. I'd like to see exactly, if somebody maybe email me exactly what you're up to there. Are you sure? That sounds like maybe I'll take a guess at it without having all the context here. That sounds like maybe that's not on the GPU node. Are you sure you're on the GPU node? If you're doing these on bridges with the rest of us, make sure you're on a GPU node. And to get to GPU node, you just type interact-GPU. You try to do any of these on any of the other types of nodes, you will end up with weird problems, of which that may be one of them. But if that's not the answer, email me and we can investigate in more detail, because it's not entirely clear just from that what's going on.
Okay, looks like a couple people had the same problem, so.
If a couple people had the same problem, then I will assume that you're not all making the exact same mistake. But on the other hand, I'm also sure that these things work pretty well. I'll give things a shot myself right now while I'm standing here. If there aren't any other questions, I'm going to go ahead and just test this myself right now. But if there are questions, let me please jump in with them, and while you've still got me live. Okay. Okay, I am training away here. So let me, just to make sure we're all doing the same thing, I'll drag that session onto the screen here. So here to step through, if you want to verify that your environment's working right, here is, let me see, here's exactly what I just did to make sure everything's working. Grab the interactive GPU. Once I got it, I went into the training example that you are hopefully working on, the MNIST directory, and I loaded the module. So make sure you're loading the TensorFlow module. That would be a different error though if you weren't doing that. Started up Python, and then to save myself typing, I just ran. You could cut and paste, but I just made sure that the CNN example that's sitting in there could run. And so I ran it, and then it extracted the data files, and then it started training away right here before I cut it off. So, so it looks to me like everything's working properly at the moment. So again, these steps right here, whoops, these steps right there. If you can reproduce those, then your environment's working right. And if you can't, then we have a more interesting problem, and let me know. But this basically makes sure that everything is working correctly.
One person said they hadn't CC'd to the MNIST directory. Looks like that was their problem.
Yes, you must be sitting there with those input files. I didn't clutter the code up with a lot of error checking in it because it would clutter the code up and obscure things. So it's not really smart about checking things like that. So you definitely have to be sitting in the MNIST directory before you try to do any of these.
All right. I'm not seeing any other questions. So if that's the case, we can go ahead and close out. Just want to say thank you, everyone, for joining us. Hopefully it was interesting. You guys got something out of it. We will send out an email with the link to the recording of this webinar. So if you want to go back through, and you guys should have access to the slides as well. If you do have any questions, please let us know. And also be on the lookout for additional Sustainable Horizons Institute's emails and upcoming events. Specifically with this webinar series, we do it quarterly, so be on the lookout for our next one as well. And we hope to see everyone there. Alrighty, thank you very much, John. We really appreciate it.
It was my pleasure. Thank you all, and see you around.